In the winter of 1977, a group of homeowners in New Mexico cut their heating bills by more than half without installing a furnace, without adding insulation, and without connecting to any new energy source. They didn't burn less fuel. They stopped needing it. The method used nothing more than sunlight, a sheet of glass, and a wall painted black. At the time, it was so effective that entire neighborhoods were redesigned around it. Universities studied it. Governments funded it. Engineers called it one of the most promising energy solutions of the decade. And then it disappeared. Not because it failed, but because the crisis that made it necessary ended. This is the story of the simplest heating system ever deployed at scale, how it cut energy use by up to 70%, and why almost nobody is using it today, even though the physics behind it has never stopped working. And by the end, you will understand exactly how it works, why it was abandoned, and how it can still reduce your energy use today without changing anything about your lifestyle. Start with the problem that forced people to rethink everything. In 1973, global oil production was disrupted during the 1973 oil crisis. Prices didn't just rise, they multiplied. Heating costs doubled, then tripled. Fuel shortages became normal. Lines formed at gas stations. In colder regions, families were forced to choose between heating their homes and affording basic necessities. For the first time in modern history, energy stopped being invisible. And when something becomes scarce, people stop assuming it will always be there. They start looking for alternatives, not theoretical ones, immediate ones. Here's what most people miss. The solution didn't come from new technology, it came from rethinking something older than electricity itself. Heat. A house loses heat in predictable ways. Warm air rises. Heat moves toward cold surfaces. And most importantly, sunlight carries energy. A lot of it. On a clear winter day, sunlight hitting a surface can deliver more energy per square meter than many heating systems produce. That energy is free. It arrives every day. And before the 1970s, most homes were designed to ignore it. The people who solved this didn't invent anything new. They removed something. The separation between the outside environment and the way a house interacts with it. The system is called a Trombe wall, named after Felix Trombe, who helped refine it in the mid-20th century. The concept existed long before that in various forms across Europe and North Africa. The design is almost too simple. A thick wall, usually made of concrete, stone, or adobe, is painted dark to absorb heat. A pane of glass is installed a few inches in front of it, creating a narrow air gap. Sunlight passes through the glass, hits the dark wall, and gets absorbed as heat. But here is the critical part. The glass traps that heat. This is the greenhouse effect. Shortwave solar radiation enters easily, but once it converts to heat, it cannot escape as efficiently. So the space between the glass and the wall heats up rapidly. Now, this is where the system becomes powerful. The wall itself is not just absorbing heat, it is storing it. Materials like concrete, stone, and adobe have high thermal mass. That means they can absorb large amounts of heat without changing temperature quickly. And more importantly, they release that heat slowly. During the day, the wall absorbs solar energy, but instead of heating the house immediately, it holds that energy inside its mass. Then, hours later, when the outside temperature drops, the heat begins moving inward, through the wall into the living space. This delay is called thermal lag. And in a properly designed system, it aligns almost perfectly with human needs. Heat collected at noon enters the home in the evening. Heat stored in the afternoon is released at night. when you need it most. So instead of heating your house when it is already warm outside, you shift that energy to when it is cold. This changes everything, because now you are not generating heat, you are managing time. Field tests in the late 1970s showed that Trombe wall systems could reduce heating demand by 30 to 70%, depending on climate and design. In some cases, homes required almost no additional heating during sunny winter periods. And unlike modern systems, there are no moving parts, no fans, no pumps, no fuel, nothing to break. The wall just sits there, doing the same thing every day. So why does every house not use this? Because the system only works if the house is designed around it. Orientation matters. The wall must face the sun, typically south in the northern hemisphere. Window placement matters. Insulation matters. The entire structure has to cooperate with the system, and that is where it collided with modern construction. After the oil crisis, there was a brief window where energy efficiency became a priority. Governments funded solar research. Architects experimented with passive design. Builders tried new methods, but then oil prices stabilized. Supply returned, and the urgency disappeared. And when urgency disappears, so does adoption. Developers return to what they knew: standardized designs, fast construction, repeatable models. A Trombe wall is not difficult to build, but it requires thought, planning, customization, and that slows things down. A developer building 200 identical homes does not want variation. They want predictability. So instead of redesigning houses to use less energy, the industry chose to add systems that produce more: furnaces, air conditioning, heating, ventilation, and air conditioning systems. It is easier to install a machine than redesign a building, and machines can be sold, maintained, replaced, upgraded. A wall cannot. This is where the shift becomes economic. The global heating, ventilation, and air conditioning industry is worth hundreds of billions of dollars. Every home built without relying on mechanical heating reduces demand for that system. A passive system removes the need for fuel. It removes the need for maintenance. It removes recurring cost, and that makes it invisible in a market built on continuous consumption. So instead of improving passive design, we improved machines. And over time, the knowledge faded, not completely, but enough that most homeowners have never heard of it, even though the physics has not changed. Sunlight still delivers energy. Thermal mass still stores it. Heat still moves from hot to cold. And a wall still works whether or not anyone is thinking about it. There is another layer to this, because the Trombe wall is only one part of a larger system. In the 1970s, architects were not just adding walls. They were redesigning entire homes to work with the environment. Windows were placed to capture winter sun and avoid summer heat. Roof overhangs were calculated to block high-angle summer sunlight while allowing low-angle winter light. Materials were selected not just for cost, but for how they stored and released energy. This approach is called passive solar design, and when it is done correctly, it can reduce total energy use by more than half, not through technology, but through alignment. The house works with the environment instead of fighting it. Modern buildings do the opposite. They isolate the interior from the exterior, and then they use energy to recreate a controlled environment inside. It works, but it is expensive, and it creates dependency. Because the system only functions as long as energy is available, a passive system continues working regardless. That difference is subtle, but it is everything. Not just how this system works, but how to apply it. The exact dimensions, the materials, the mistakes that make it fail, and why a method that once cut energy use in half is now being quietly rediscovered by architects who are building homes that cost less to run than they did 50 years ago. And more importantly, how you can use the same principle even if your house was never designed for it. Now we get into the part that most people expect to be complicated. It is not. The entire system comes down to 3 variables: surface, mass, timing. If you understand those, you understand everything. Start with the wall itself. A proper Trombe wall needs thickness, not decoration, not drywall, mass. Typically between 8 and 16 inches of material like concrete, brick, or adobe. The reason is simple. Thin materials heat up quickly and cool down just as fast. They do not store energy. They react to it. A thick wall does the opposite. It absorbs energy slowly, holds it, and releases it over time. That delay is what makes the system useful. Without it, you are just heating the house during the day when you do not need it. Now add the glass. This is where most people make their first mistake. The gap between the glass and the wall matters. Too wide and heat escapes. Too narrow and airflow becomes restricted. The sweet spot is usually between 2 to 4 inches. That small space traps heat efficiently while still allowing controlled air movement. Because yes, air movement is part of the system. Some designs include vents at the top and bottom of the wall. As the air in the gap heats up, it rises. Cooler air from inside the house is pulled into the lower vent, heated, and returned through the upper vent. This creates a natural convection loop. No fan, no electricity, just physics. But here is the important detail. Those vents are optional, and in colder climates they are often avoided. Because while they move heat faster, they also lose heat faster once the sun goes down. A sealed system stores heat better. A vented system distributes heat faster. That is a trade-off, and most modern implementations choose storage over speed. Now, orientation. This is not flexible. If the wall does not face the sun, it does not work. In the northern hemisphere, that means facing south. Even a deviation of 20 to 30 degrees can reduce performance significantly, because winter sunlight comes at a low angle. If you miss it, you lose the entire system. This is why the method disappeared from mainstream construction, not because it failed, but because it requires alignment. Modern housing developments are not designed around the sun. They are designed around roads, lot divisions, and maximum density. So even if you understand the system, you often cannot use it fully. Now, let's talk about the timing. This is where the system becomes precise. A well-built Trombe wall has a thermal lag of about 8 to 12 hours. That means the sun hits the wall around noon and heat enters the house between 8 p.m. and midnight. That is not accidental. That is the goal. If your wall is too thin, the heat arrives too early and you end up overheating during the day. If your wall is too thick, the heat arrives too late and you lose it before you need it. So the system is not just about collecting heat. It is about delivering it at the right time. Now here's the part most people overlook. Summer. If you build this system incorrectly, it will overheat your house, because the same wall that traps heat in winter will trap heat in summer. This is where shading becomes critical. A properly designed roof overhang blocks high-angle summer sun, but allows low-angle winter sunlight to reach the wall. This is not guesswork. It's geometry. At higher sun angles, the overhang casts a shadow. At lower angles, sunlight passes underneath it. So the same wall that heats your house in winter does nothing in summer. No switching, no controls, no adjustments, just design. Now let's address the biggest misconception, that you need to build a new house to use this. You do not. You can retrofit parts of this system, not perfectly, but effectively. For example, a simplified version can be created using a sun-facing wall, a dark surface, a glass panel placed a few inches in front. Even this basic setup can create measurable heat gain. It will not replace your heating system, but it can reduce how often it runs. Another approach, thermal mass inside the house. Materials like brick, stone, or even water containers placed in direct sunlight can absorb heat during the day and release it at night. This is the same principle, just applied differently, and it works. Now step back. This is where everything connects. The Trombe wall is not just a trick, it is a reminder that energy efficiency does not always come from producing more energy. Sometimes it comes from using what is already there. The 1970s forced people to think this way because they had no choice. Today, energy is available again, so the urgency is gone. But the math has not changed. Sunlight still hits your house every day. Heat still moves the same way. Materials still behave the same way. And a wall still does not need maintenance, fuel, or replacement. So the real question is not whether this works. It already did, at scale, under pressure, with measurable results. The real question is, why did we stop designing buildings that reduce energy demand and start designing systems that increase it? Because once you see that shift, you start noticing it everywhere. And once you understand that, you stop looking for better machines and start looking for better systems. If this made you think differently about how buildings actually work, leave a comment and say one thing. Would you redesign your house around the sun if it cut your energy bill in half? Because the answer to that question tells you everything about where the future of housing is going. Thank you for watching this video. Click here to watch another video that might interest you.